Hello. Now that we know how to determine if a series converges, we need to validate that Taylor series converge to the function we expect, or if we use a polynomial to approximate the value of the series, how accurate is that approximation? If we have a geometric series, we know that a finite number of terms in a geometric series excludes another geometric series from the sum, and so we could say exactly how close a finite number of terms would be to the infinite sum if our series is geometric. For non-geometric series, we're looking at that difference without using technology. We could take any polynomial, use its value to approximate a series value, and then use our calculator to check the difference and see how small that difference could be. Our job is to find a way to put a bound on that difference even without using technology. So the first thing we're going to look at, we're going to revisit our alternating series. And we use that number line to visualize what was happening as our alternating series zoomed in on its limit. We saw that our first term overshot our limit if our first term was positive. And so we know that our first term differs from the limit by a set amount, but we don't know how big that amount is. If we look at adding in the second term, though, we can now say, oh, our first sum was off from our limit, but was off by less than the value of the second term, because the second term took us back to the other side of the limit. This was A2. So S1 differed from our limit by less than A2. And if we throw in a third term, A3, we again get closer to our limit. But how far was S2 from our limit? I don't know exactly, but I know it was less than A3 in absolute value. S2 was less than our limit, S1 was bigger than our limit, and S3 will again be greater than our limit. How much greater? By less than S4. And so we have what's known as the alternating series bound, the alternating error bound, and that tells us that S sub n will differ from our infinite limit, from the limit of our series, when said series converges, by less than the absolute value of the next term in our series. In fact, we could use the sign of that next term to determine if our sum was too big or too small. Let's look at an example of how this works. If we want to estimate the error in using the third order Taylor approximation for ln of 1 plus x to get a value for ln of 1 plus x. In other words, if we use the Taylor polynomial, we'd get a value. How close would that value be to the actual value of ln of 1.5? Recall the Taylor series for ln of 1 plus x to be, we'll use our third order Taylor polynomial, and that third order Taylor polynomial would be x minus x squared over 2 plus x cubed over 3. And we want to evaluate that for an x value of 0.5. Notice we're looking at the series for ln of 1 plus x, so 1.5 is 1 plus 0.5. So we're interested in what is this approximation value at 1.5? How close is it to the actual value of ln of 1.5? You can confirm that 0.5 is in fact within the interval of convergence for this series. Since this will be an alternating series when we plug in 1.5, or 0.5, we get to look at our error using the alternating error test. Again, we're looking at absolute values, so we really are not concerned with whether the next term is positive or negative, but we are looking at the next term being x to the fourth. And so we can say our error will have an absolute value less than x to the fourth, and our x in this case is 0.5 over 4. As a fraction, that's 1/64th. Just for curiosity, as a decimal, that's 0.015625, I believe. In fact, if we compare this, if we plugged in 0.5 to our approximation, we would say ln of 1.5 is approximately, plugging 1/2 into this series, we get 5/12. And so what we're saying is that our approximation is, in fact, within 1/64 of 5/12. And as we go further out in our Taylor approximation, that error gets smaller and smaller. And so we would be able to confirm that with this alternating series, our polynomial, as our polynomial order increases, approaches the series we expect, ln of 1 plus x. What about series that don't alternate? We need to, again, generalize, get a little less specific. So let's look at our general Taylor series f of x at the series about x equals a. So that Taylor series would be f of a plus f prime of a times x minus a plus f double prime of a x minus a squared over 2 factorial. We go out to the nth term, the nth derivative at a times x minus a to the nth over n factorial. And that would continue, and let's call everything in the continuation r sub n. That's the remainder after, if we stopped at a polynomial of nth degree. We'd have all this extra stuff. Well, if we can show that that extra stuff dwindles away to virtually nothing, then we know we have, in fact, equality not just at x equals a, but for more values of x. And we'll be able to say exactly what values of x, depending on how quick, when and where that remainder goes to 0. It turns out this remainder has a very nice value. And that remainder is, in fact, the next derivative evaluated somewhere times the next power of x minus a over the next factorial. Looks a lot like our next term in the alternating series test. But the condition is we need to find this next derivative somewhere. And that c value is somewhere between x and a. Usually we can't find an exact value for c, but we don't have to. We just have to find a value that bounds this expression. If we can find something, this expression has to be smaller than, and that expression goes to 0, then our expression will go to 0 as well. For example, if we have an increasing function, we might use the derivative at the right endpoint of the interval of x's we care about, because we know then our value will be greater than or equal to all the other derivative values. Or if we had a decreasing function, we could use the left endpoint value. If we had, for example, sine x as our function, we could use 1 as a value that is greater than or equal to all other values of sine. We call this error the Lagrange error. And our job is just to find a value that this expression has to be smaller than, and then we know that we can confirm that our Taylor series does in fact converge to the functional values we need. And we can also find just how accurately a Taylor polynomial is to our functional values. Let's look at an example. If we're looking at the Taylor series for e to the x, or the Maclaurin polynomial for e to the x, the second order polynomial, and we want to see the values we get using this polynomial give us a certain degree of accuracy on an interval. So on the interval from -0.1 to 0.1, will the values we get from the polynomial be accurate to 3 decimal places, which is pretty good when you consider how small a degree polynomial we're dealing with, how small the degree. So second order polynomial for e to the x, our second order Taylor polynomial would be 1 plus x squared over 2 factorial, or x squared over 2. This doesn't alternate, so we can't use the alternating series error. We'll use the Lagrange error. So our job is to note that our error, the absolute value of our error, will be less than or equal to that Lagrange error expression. I'll write that down again. The n plus first derivative somewhere times x. Now our a in this case is 0. So I'll just write x n plus 1 over n plus 1 factorial. And what would be a derivative that would be greater than or equal to all the derivatives on this interval? Well, all the derivatives of e to the x are e to the x. That's an increasing function. So on this interval, I'll find the greatest value for that derivative at the right endpoint. So I'm going to use e to the 0.1 to give a bound on this derivative. What about the x values in this interval? Well, the x values that would give us the greatest value of x to the, in this case, third power would be 0.1. Since we're doing absolute value, negative 0.1 would also work. 0.1 cubed over 3 factorial. So our error will be less than this, and we wanted our error to give us 3 places of accuracy. What would that mean? Well, we need things to round off to 3 places correctly. So we'll make a note that we're looking for an error less than 0.0005, so that things, if they were correct to that place, then they would round correctly to 3 decimal places. Is the error we computed less than 0.005? Well, we know that e to the 0.1, well, e itself is less than 3, so e to the 0.1 is definitely less than 3. So this is less than 3 over 3 factorial times 1,000th. And 3 over 3 factorial is, in fact, 1/2. So yes, indeed, we get the accuracy we're looking for. This expression is equal to the 0.0005 we were looking for. In fact, it's a lot less because e to the 0.01 is a lot less than 3. So we definitely have the accuracy we were asked to confirm. I have a table of values that will help you see just how good our approximations are. If we look at x values between negative 0.1 and 0.1, we see the computed values of e to the x versus the computed values of our second degree Taylor polynomial. And we see the differences are well within our 0.0005 boundary. In fact, they're about a third better than that kind of accuracy. So why don't you go practice finding alternating series error, Lagrange errors to determine how accurately Taylor series converge.